Thank you to the organizers for inviting me to be here. It's a real pleasure and an honor to present these events. So,
talk on binary black hole detections in 0102.
Great, thank you. All right. Thank you to the organizers for inviting me to be here. It's a real pleasure and an honor to present these events. So you'll notice that I don't have the little on behalf of the LSC and Virgo collaborations. This is partly a review of some of the results, but I'm really going to highlight some of the kind of short author work that we've done with some of the binary black hole detections from the first few events. So I'm not giving this on behalf of the collaboration, but I'm going to highlight some of the binary black hole results that we have so far and what I find interesting about them. So here is where we ended the first observing run from LIGO. These are the 3 binary black hole mergers from 01. So you'll notice the different lengths here. So obviously the axis here goes a few hundred million years that way. But what I'm showing here are the final stages of the in-spiral and merger of the events that were visible in the LIGO band. So that means that all of these here are right where the signal roughly crossed into our band of sensitivity, and for that I use 30 hertz. So this is 30 hertz to merger for all of the events. As we've been hinting, I think people have mentioned already, the merger rate here, so basically how high of a frequency the black holes merge at kind of determines how long they spend in band. As you go to lower masses, you merge at higher frequencies, therefore those signals spend longer in band. So you can take the length of these signals on this figure to give you a rough idea of how low of the mass these binary black holes had. So these are the first events that we had in 01, and then so far that we've published in 02, we have these extra few events here. So we had 170104 in January of last year. We had an event in June, and we had an event here in August. And so this rounds out the binary black holes that we've published so far on the first and second observing runs from LIGO, and so this is where I'm going to be digging into some of the details. So a lot of these details have already shown up in this conference, so I'm kind of giving a little bit of a review of some of the constraints that we have from LIGO so far, reviewing stuff that we've already talked about these last 2 days. So this figure has been shown. This is the kind of cartoon mass diagram of the binary black holes. 150914 was obviously the first and exciting one, a massive one, and some of these other events have been starting to reach closer to the black hole masses that we had kind of expected from our observations of X-ray binaries. So over here, 151226, this is one of the more exciting ones so far for a few reasons that I'll get into, but so far it's looking like a pretty self-consistent population. Before I get into some of the individual details here, there's been some questions that have come up in the last 2 days, and definitely questions that I've encountered over the last few years of talking about these results. And one of the very common questions is what lies below our threshold. So we talk about these GW, these gold-plated gravitational wave events. We've got this one trigger that we talk about as LVT, standing for LIGO Virgo trigger, hinting that we're not quite as confident, but what does that mean and why aren't there more LVTs? People's intuition generally leads you to expect there to be a whole lot more events just below threshold than we're seeing above threshold. So what gives? And this is the short answer. So this is our figure that shows basically how we define our confidence in events. This is from the 01 summary paper for the binary black hole mergers in 01. And on the left, we have results from the PyCBC search, and on the right, we have results from our other compact binary search, GST-LAL. And here, what we're showing is a cumulative distribution, where cumulative is going in this direction. And in black, we're showing the background here. So this is artificially sliding the detector data for the 2 LIGO detectors in time, greater than the light travel time between the 2 instruments, and generating the statistics for what our background looks like. So things that that operate completely independently in the 2 detectors that are basically terrestrial noise. We can simulate years and years and years of advanced LIGO operation and ask how often do uncorrelated noise events happen to be coincidentally aligned in time and in template space to give us basically a noise event that is a coincidence and looks like a gravitational wave event. And so that's what's generating this background here. Where intuition comes from is more about what we refer to as SNR, signal to noise ratio. And so as we go along here, you're looking at, so this is a very loud event, 150914, and then we go to lower SNR events here. So this is the zero lag distribution here. This is showing our signals. And now I'm going to show a slightly different version of this. So this is the, come back. All right, so this is showing the model employed by GST-LAL for modeling the foreground and the background. So here we have our events. These are all part of our signal model. Here we have our noise model, the background. And so as we scale back in this likelihood statistic, the detection statistic for GST-LAL, we're going to lower and lower SNR. And then right around LVT 151012, we hit a wall. And this wall is our background. And that is dominated by not the Gaussian parts, not the thing that you think of with signal-to-noise ratio, but the non-Gaussian artifacts in the data, the glitches, the non-stationarities. Those are really driving our background and are causing us to hit this wall here. So basically, once you start going a little bit below threshold, we hit a very large background from non-Gaussian features. All right, going back to the parameter estimation here. So this is showing the mass distributions for the O1 and O2 events that I've shown in the previous slides. So this is primary mass, the mass of the most massive object on the x-axis, and secondary mass on the y-axis. Down here, this is 15/12/26 Boxing Day event. This is the January event up here. This is 1509/14 up here. So a few things that you'll notice in this figure. We have these kind of two characteristic shapes. Down here we have bananas, and up here we have not bananas, so slightly straighter regions. What's that? Papayas, perfect. All right, so we have bananas and we have papayas. So the bananas here, as you've probably heard before, are following lines of what we call constant chirp mass. So this is basically a line following a constant value of a certain multiplication of the two component masses that enter the post-Newtonian expansions at low order. So that's what we are really sensitive to in the in-spiral. And so the events that spend a long time in band that we see a lot of the in-spiral for, we constrain, basically the low mass events, we constrain the chirp mass very well, and we don't constrain the other mass component, the mass ratio, very well. So we get these bananas, and the extent of the banana away from this equal mass line is decided by our inability to measure mass ratio. And that's driven by a few things, one of the most important being degeneracy with spin. As you go toward higher mass, we see less and less of that in-spiral. We see more of the merger, and the merger gives us information about total mass. So then you see us starting to change from lines of chirp mass from the bananas to lines of constant total mass, the papayas. And that's where most of our mass constraints are so far. But one other thing to notice is that so far, all of these posteriors have non-zero support at the equal mass line. So far, we can't say for any of these events confidently that we've measured some unequal mass ratio. So far, they're all consistent with equal mass. All right, so now looking at spins, go back. So these spin disk plots have shown up in a lot of our papers. I'll spend a little bit of time giving you some intuition for what this actually means. So on the left is representing our information about two parameters that go into the primary spin. So that's spin magnitude and the spin misalignment with the orbital angular momentum. So down here, this is 0 spin magnitude. Up here is maximal spin of 1 and aligned with the orbital angular momentum. And then the arc as we move down here is misalignment with that orbital angular momentum. And so this is actually a histogram, and these bins change in size to give equal weight, equal prior weight to each one of those bins. And so right now what I'm showing you is our prior, which is uniform in this binning, and our prior is uniform in spin magnitude and isotropic in orientation. So now looking at the first event, 150914, we see here the constraint for the primary spin, and over here the constraint for the secondary. And what we can say confidently, so again, these bins are chosen to be sized so that they have equal prior weight. And so you can think of any changes from being completely smooth here being driven by actual information in the data. And so what we can say looking at this is that we seem to rule out the possibility of extreme spins that are aligned with the orbital angular momentum and extreme spins that are anti-aligned with the orbital angular momentum. And so this is something that we can say from the first event alone, is that not all black holes are extremely spinning and aligned, just from the gravitational wave data alone. LVT 151012 is kind of a similar picture. So one thing you'll notice is there isn't quite that same symmetry that we saw for 150914 for the constraints of the two spins. If you think back to that mass distribution plot that I showed, the extent of the banana was pretty large for LVT 151012, meaning we didn't constrain mass ratio very well. And if you were to marginalize, so here we're marginalizing over all the other parameters that we're not looking at, all the parameters besides spin. And so when we marginalize over masses, a lot of posterior weight is put at unequal masses. And so once we start moving away from equal mass, then we get more information about the primary spin than the secondary spin, which is why we get more of the prior back on the secondary spin. But basically, the answer is the same. We're ruling out these extreme aligned and anti-aligned scenarios, getting a lot of posterior weight kind of down here in the either low spin or in the plane, potentially high spin. Not necessarily, exactly, not the secondary. So only because of our uncertainty and mass ratio, we can only say things confidently about the primary for that event. And then 15, 12, 26 is one of the most interesting so far in that this is a pretty good constraint from the data. We again can rule out high aligned and anti-aligned spins for the primary, but now we can, for the first time, rule out zero spin. And so what we are saying here is that we have pretty high confidence that there was at least one spinning black hole in this binary. And so actually, if we were to look at a different projection of these spins, instead of looking at these individual primary and secondary spin disk plots, if we were to look at instead a two-dimensional marginal distribution for the spin magnitudes of the two black holes, then we can rule out that both of these, the possibility of both of them being non-spinning. So one of the statements in the paper is that we know that the slowest spinning black hole in this binary had to have a spin greater than 0.2. All right? Okay, so now I've been showing these spin disk plots, but we've talked a lot these last 2 days about effective spin, and there's a good reason for that. That's what enters early in the post-Newtonian expansions. That's the thing that we actually best constrain here. And in some ways, these spin disk plots are basically giving kind of easier to interpret projections of the information that's implied by a constraint on the effective spin. So I'm going to now go through the effective spin constraints here. So for 150914, on the y-axis up here is chi effective. So that's this mass-weighted combination of the aligned components of the spin that we're most sensitive to. And on the x-axis here is showing an effective in-plane component of the spin. So this is also a mass-weighted combination of the spins, but in the plane of the binary. And so here we're getting a fairly tight constraint on the effective spin. So again, our priors are uniform in spin magnitude and isotropic in orientation. So the prior that implies on chi effective is actually peaked at 0, but it has much fatter tails than is shown here. So this is data constraining the effective spin to be closer to 0 than to be in these extremes of -1 and 1. But down here, we basically recover our prior. We get very little information about the in-plane component of the spins here. And so right now, this is effective spin, consistent with an effective spin of 0, so this is constraining it to be small. And as we go through the events, it's going to be a common theme. So for LVT 15, 10, 12, again, we constrain the aligned component, the mass-weighted combination of the aligned components of the spin to be close to 0. And we get roughly our prior back on the in-plane component of the effective spins. For 15, 12, 26, I need to stop using this thing. Go back. For 15, 12, 26, we get a constraint that is, for the first time, away from 0. So looking at the effective spin of 0 here, we're ruling that out. Again, we're basically getting our prior back on the in-plane component of the spins. This is a slightly different shape, but it's basically consistent with our prior, conditioned on this measurement of a non-zero chi effective. So really, these constraints on the spin of 15, 12, 26 are being driven by our measurements of the effective spin. Now on to the next event, so 06, 08. This is, besides being fancier in color, basically a very similar picture to a lot of the other events we've looked at. Again, this is consistent with a 0 effective spin. So this is really starting to hint at some underlying feature of the data here. So we're really starting to see a void of events at these extreme effective spins at kind of close to 1 and close to -1. And we're, again, not getting much information on the in-plane component of the spins. And rounding out with 0814, again, a similar picture, consistent with 0 effective spin, and getting our prior back on the in-plane component of the spin with some maybe constraints away towards higher values, but still very uncertain. Okay, so all of these results that I've been showing you are the result of our kind of one step, if you think back to Neil's talk, our one-step approach to analyzing the posterior for the data. So these are the probability density functions that I'm showing over here, the posteriors. And theta here represent all of the model parameters that are going into our analysis. So those are the masses, the spins, et cetera. And d here is our network of gravitational wave data that we've collected. And so I'm putting the prior here suggestively in red because this has received some negative attention, as most Bayesian analyses tend to receive, in that we have to make choices about our prior here that we use in our Bayesian analysis. I've said that we use a uniform in spin magnitude, isotropic, and orientation prior. And that has implications on what our effective prior is in the effective spin. And the next step is really to try to take this population of binary black holes that we're detecting and start to learn something about the underlying astrophysical population that's giving us these events. And so now we're going to add a step into this and remove these choices of prior for individual events that I've been showing so far. So basically, I'll just go on to the next slide. This is our new posterior. So this is an updated version of what I showed in the past. And so here you'll notice something that looks a lot like the likelihood that I showed on the previous slide. So this is where our data comes in on individual events. So I here is indicating a particular binary black hole merger. And this is the likelihood that we've used in the past. But now we don't have that P of theta anymore. We don't have that uniform in spin magnitude, isotropic, and orientation spin prior that I showed on the previous slide. We're replacing it with this new a hierarchical prior. So now this is basically, alpha here is now giving us parameters to a population model. And so these are parameters that are potentially describing something physical, so not just this assumption of uniform in spin magnitude, for example, that I've been talking about in the past, but replacing that with a physical prior that we want to actually constrain, parameters that we want to constrain to use something to learn about the population of binary black holes that we're detecting. So you take out the kind of arbitrary prior, you put in a physical model for your population. That now has a prior, you can't avoid that. But this now gives us a way to combine information from multiple events to take out that uniform in spin magnitude, isotropic, and orientation prior that we used for our single events and put in something more physical and start constraining the properties of it. And so that's what we do. So up here, you'll notice I use a prime to break the Farr degeneracy. I am Farr prime. This is Will Farr over here. So the first Farr paper on this spin population modeling in 2017, in that paper, so Ilya was on that paper as well, Alberto was on there as well. We basically used a few very simple fiducial models to describe the underlying populations that might be indicative of interesting things. And so one of the nice steps here is that we focus just on effective spin. So we say that the data really constrain to first order, the effective spin. So let's focus on what information we can extract from the effective spin to learn about the population that we're detecting. And so here there's two types of populations we consider. One being aligned. So in this case, we mean kind of perfectly aligned spins. And the other being isotropic in spin orientation. And then we think of a couple of different possible spin magnitude distributions. So again, fiducial simple models. So we use a low spin prior, which is basically a low spin magnitude distribution, which is basically a linear spin that's high at zero spin and falls off linearly to be low probability at high spins. We use a flat spin magnitude distribution, and we use an increasing linear spin magnitude distribution. And so that's how we get these different populations here. And so the isotropic ones are all here. They're symmetric about a zero effective spin, as you'd expect for an isotropic population. And then the aligned populations are all over here and only have support for positive chi-effective measurements. And so this is something that Ilya showed already, which is the result of running this analysis. So basically, you use these zero parameter models, these fiducial models, you fit them to the data, to the full population of binary black holes that we have so far, and you just do some evidence, basically some evidence ratios, and get out the Bayes factors here to sort out these various models, see what the data are hinting at. And so far, they are really, as you might have guessed from those individual events that I showed you so far, they rule out pretty strongly this possibility of high and aligned. But a lot of these other odds ratios are a little bit more equally balanced. They're not quite, the data don't quite rule out all of these models yet. And so this is hinting at the data starting to be informative, but as Ilya mentioned, this analysis is a little bit insensitive if we're in the scenario where spins are low. So all of this information is really kind of making this assumption about these spin magnitudes that I'm showing over here. And we're not going to be very sensitive with this type of technique unless we actually put in a low spin model to try to sort out that possibility. And so the next Farr paper on spins, so I'm at the front of this one, is now implementing a different model with the hope of not having as much insensitivity to the scenario of low spin magnitudes. And so it's another type of simple approach. So now the general motivation behind this approach here, so this is me, Dan Holtz, and Will Farr on this paper. And instead what we do is we really try to focus on that key characteristic of an isotropic population being a symmetry about a chi-effective of 0. So if the population of binaries is isotropic, regardless of the underlying spin magnitude, we expect that chi-effective distribution to be symmetric about 0. If it's a field formation scenario or a chemically homogeneous formation scenario, we expect some amount of preferential alignment of the spins, and we expect it not to be, the underlying distribution to not be symmetric about effective spins of 0. We expect most, if not all, events to have positive chi-effective measurements, which is also what was kind of being hinted at in the previous paper that I showed. So the simplest model we could think of to look for this is a 2-bin model, so 1 parameter, and we fit that to the data. And so first we ran it on some simulations to make sure it behaved as we expected, and it didn't. So this is a population of binary black hole mergers, 250 events that we simulated from on this green part here, an isotropic population, and in blue, an aligned population. And this is showing the posterior recovered for that fraction here, for the height of the chi-effective is positive bin. And so let's look at first this isotropic population. So in this case, we expect symmetry about chi-effective of 0. We expect that fraction of events with positive versus negative chi-effective to be 1/2. And so here is the true line for the green distribution, and the posterior we get back is consistent with that. So that is behaving as expected. But over here, this is now simulating an aligned population, simulating a perfectly aligned population. So all effective spins are positive, but yet when we analyze the data, when we take 250 events from this simulation and we run it through our single parameter model here, we get a posterior distribution that's peaked well away from the true value, which for this case is 1 here. And so the reason this is failing is the same thing that the previous analysis that I showed was insensitive to, which is having a low spin population. So here we simulate spin magnitudes with a half normal distribution of a width of about 0.01. And so what's important there is that the underlying distribution of physical spins, so true chi-effective values here in this case, is much smaller than our statistical uncertainty on the measurements of individual chi-effectives. And so in that case, this model kind of breaks down because basically all of our events are falling on this border between bins, and the math just kind of works out that you get this, you get fooled into thinking you might be looking at an isotropic population when it's not actually true. So we got a little bit more complicated. We added in 1 more bin. So now we moved to a 3-bin model. And we now use that model. There we go. So this is our new 3-bin model. And so what we do is we add in this tiny little narrow bin to basically soak up the uninformative events. So where we're failing is having these events right on that border. And when we can't distinguish those spins, when they're too close to 0, we call them uninformative. And the height of this bin is just going to tell us what fraction of our population is basically uninformative. And then the remaining events can help us to separate out whether this chi-effective distribution is actually symmetric about 0 or not. And so now this is the same population that I simulated before of these really low spin events. And this is the posterior in blue here on the fraction of informative events with positive chi-effective. And we basically get out our flat prior here as we would expect. And in the dashed green line here is showing the posterior distribution basically on the height of this bin, or sorry, on basically what's left over after we account for that bin. So it's saying what fraction of events are actually informative, and we say close to 0 of these events are informative. So this model is actually able to handle the case of low spin, say that there's a lot of events, but none of them are very informative. And so if we're trying to infer whether this distribution is symmetric about a chi-effective of 0 or not, we rightfully say we don't know. All right. So we'll blaze ahead here, and I'll show you the results on the first few events, so this is O1 plus the January event. In blue here is the posterior distribution on this fraction of positive events. And so basically, if you were interested in all aligned, or all positive chi-effective, which isn't the same thing necessarily as all aligned, that value is over here. And if you're interested in isotropic, that value is over here. And if you want to just compare those two possibilities, you take the ratio of those probabilities, and you get a ratio of about 1.1. So the data aren't informative yet, which isn't all that surprising. But it's starting to be suggestive. So this is now, OK, you assume that you know the spin orientation distribution. Then you can use these chi-effective measurements to directly probe the distribution of spin magnitudes. And so now what I'm showing here is if you assume everything is aligned, this is the distribution you get out on underlying spin magnitudes. So if you're very, very convinced that your population synthesis model produces positive chi-effective measurements, if your binary population synthesis model produces positive chi-effectives, you fall into this particular case here, and you can start to say already from the data that we've collected that spins must be low. All right, so if you have strong prior assumptions that spins are aligned, then we can already say from the data that it looks like spin magnitudes must be low for these black holes. But if you are convinced that isotropic is a possibility, then we get very little constraints on spin magnitude so far. All right, so with that, I will stop here and take any questions you may have. Thank you.
First, thank Ben. And anyone who's spun down fast enough can ask a question. Yes.
So I do have a question about the priors still, sorry.
Okay, great.
So all the standard results, in fact, all the results I know in Bayesian theory for consistency and convergence of posteriors depend on the parameter space and on the prior distributions having certain properties, and yours don't. And so I'm curious. So you can't guarantee consistency and convergence for your posteriors, given the priors and given the nonlinearity of the parameter space. And that's a problem even for the hierarchical Bayesian model, because you can't guarantee that in the real population there's not going to be some biasing. So I'm curious. Have you tried the analysis starting from several different priors and seeing whether they still converge?
Sorry, by convergence here, when you say convergence, I usually think of like a Markov chain Monte Carlo sampler converging on the posterior distribution. But I think you mean some form of bias that you're concerned about.
Yeah, minimal insensitivity to initial prior.
Okay. So we are sensitive to choices in priors, but what is nice about the hierarchical modeling is that we're now pushing the potential arbitrariness of prior choices that we, in this case, don't really have a good motivation to define into now a population model instead of the underlying prior that's going into each of these single event analyses. So I've been mentioning the typical prior that we use for our single event analyses, this uniform in spin magnitude, isotropic in orientation. That's a pretty, strong prior in effective spin, which is what we often are now looking at and looking at what the data are saying about these events. And so what the prior that we are now less sensitive to is that choice in the spin magnitudes prior. But now we're specifying priors in the case of this bind approach, for example, is a prior on those bin heights. And so sometimes it's a little more palatable to be specifying uniform priors in the bin heights of this underlying model in that it's an actual physically motivated model in some ways that's starting to tell us something about the data. But we are still sensitive to our prior. Our constraints from the data are minimal so far. And so we could change the priors here and probably see a pretty good change in the posterior results. But at least now we've pushed this, I think, into an easier to interpret set of choices for priors for this case.
I'd like to ask a question.
Yes.
Given what we know from black hole spins that have been measured separately from gravitational waves, they seem to have high values. So wouldn't that put in as a prior maybe your second option?
The second option, yes. So if you have strong prior, so another way to phrase these results that I've been showing is if you have strong prior assumptions that black hole spins have to be large, then that means that that we are seeing evidence that it must be an isotropic population. That's very true. So it depends on where you want to put your money. If you think that things are aligned versus isotropic, if you think they're high spin versus low spin, we can start getting information out from the data in that way.
Question from Ramesh.
Oh, here first. Sorry. So it seemed that the LIGO spin constraints for the lower stellar mass black hole mergers like 151226 and 170608 tended to be tighter than the heavy stellar mass black holes. Is it because they live in band longer?
Yeah, so we get a longer fraction of basically more SNR is coming from the in spiral, which is where that spin is actually encoded.
Okay.
Yeah, so going back to the beginning of your talk, you were explaining what these LVTs are.
Yes.
You still didn't answer, I think, the question that people were asking. How is it there's only one LVT and we have got so many detections? Are you not reporting them all, or is it reasonable that there should only be one?
So I guess I can let Duncan speak up here. He spent a little more time thinking about this than me, but.
I'm no longer a LIGO Scientific Collaboration
Yes.
member, but I haven't forgotten everything I once knew. So the issue is, Ben kind of alluded to this on the plot, that when you look at the background, the false alarm rate drops 3 orders of magnitude for every 1 unit in SNR, right? And the SNR scales linear with the distance. And I think for an isotropic population, the SNR goes as like 1 over rho to the 4th, I think, is the universal distribution from Bernie's paper.
Yep.
So you have a fairly shallow distribution from the population you expect, and an extremely steep drop from the background. And it's not the non-Gaussianity. I mean, that's the limit. The searches are very close to the Gaussian limit. There's not a lot more we can squeeze out. So there's a very, very small shell of the universe where you go from 1 sigma to 5 sigma. That's the reason. We're not, well, maybe you are, but I don't think the LSC is hiding a bunch of like 2 sigma things. It's a very, very small.
Right.
I think we have to stop there and thank Ben Farr, Farr Prime,